Hi everyone, welcome to another exciting episode of Linearity 2 videos. Rahana and I today are going to be starting to talk to you today about some more stuff around finding minimums and maximums, or if we sort of want to connect back to the theme that we're dealing with in this part of the class, the sort of idea of how do we actually optimize an objective function. And we want to optimize an objective function when it's not a linear function, right? So we're actually interested in sort of nonlinear functions. How do we go about finding maxes and mins for that? And in the videos we're going to put together for you, this first one we're going to deal with doing that from an analytical perspective. So we'll be making some connections back to what you learned in one-dimensional calculus. And then we're also in a subsequent video going to talk about more of a computational approach for doing that lines up with some of the reading that you're going to look at as well. But first, let's start with the analytical approach. And to do that, we're first going to start by just thinking about one-dimensional calculus and doing a little bit of a refresher on how we think about maxes and mins in one-dimensional calculus, maybe again making a bit of a connection that might not have been clear to you in the past. So in one dimension, how do we actually know if we have a max or a min? So Rahana, how do we know if we have a max or a min in one dimension?
Well, you set a derivative equal to 0.
Okay, so one thing I need the derivative of the function with respect to whatever my variable is. It's a single variable function, so this is f of x, to be equal to 0. So that's necessary.
But not sufficient.
And what else do I need?
Then you look at the second derivative.
Okay, and then I need the second derivative with respect to x squared to be what?
You look at the sign. If it's positive, then you have a minimum. If it's negative, you have a maximum because you're like an upside down parabola.
So positive derivative indicates positive curvature. So that means if I had a derivative that was 0 and a positive second derivative, I'd be sitting there. Minimum, I'd be sitting like that.
Mm-hmm.
And what if it's equal to 0?
Then you're not sure. You could have an inflection point, like if you're x cubed.
So it could look like that.
Yeah. You could have a min, like if you're sort of like x to the fourth.
So it could be like this, if we're x to the fourth. And I want to take a minute and ask you about that, because this is sort of an interesting phenomenon. Why is it that this happens with x to the fourth? Why is this not sufficient to actually find that minimum?
So what's going on at these minima and maxima is roughly that the second derivative is telling you something about a quadratic approximation, a second degree approximation, like in the Taylor expansion of your function, if you could just stop after the second degree.
So if we actually write out a Taylor expansion of the function about this point, let's call this point x0, right? Then let's see, that's f of x at x0, right?
Yes.
Plus
some term with the first derivative.
The first derivative evaluated at x0 times x minus x0, right? Plus the second derivative evaluated at x0 times x minus x0 quantity squared, and I think I need a 1/2 out front.
Right.
Yeah. And
plus
so on.
Dot.
Right?
Yeah. And with these, you have this much gives you a pretty good approximation, but with the x to the fourth, you really need to go all the way out to the fourth degree to get some information. Right.
So there's this sort of interesting connection between this sort of Taylor approximation of the function and assessing whether or not the function actually is at a minimum or a maximum. And so if this Taylor approximation is good enough, then this test is good enough to tell you. Okay, great. So we know how to find a minimum or a maximum with a sort of function that we can analytically take the derivative of in one-dimensional. Let's move on to sort of n-dimensional. So I'll take that plus and move it over there. And in class, last time we talked a little bit about sort of the rules for mins and max. So one of the things you know is if you want to be at a min or max for an n-dimensional function, you know something about what the gradient is, right? The gradient of the function evaluated at that point has to be 0. That's a necessary condition for a minimum or a max, so long, of course, as the function is well behaved, right? As long as it's a smooth differentiable function.
Everything has to be very differentiable.
Now, I'm sort of tempted, Rahana, to propose, so that clearly this is like directly connected, right? Just like the derivative is 0 here, the gradient is 0. It seems like basically the same rule, but just in higher dimensions. So how about this for a rule? I'm going to propose a rule to you. What if we said the partial with respect to, so this is a vector, right? So this is the gradient of a function which depends on x, and x could have 10 components or 7 components, whatever.
Sure.
So I'm going to say the partial with respect to x sub I squared has to be greater than 0 for all i's, right? So this is like saying if I had a two-dimensional, the partial with respect to x squared has to be greater than 0, the partial with respect to y squared has to be 0.
Sure.
If that were true for every I, then I think that would mean I was at a max, because that would say that I would look like a parabola with respect to sort of x1 or x. I'd also, if I sort of took a cut in the other direction along the y direction, it would also look like a parabola. And even if I was in 10-dimensional space, as long as that second derivative was greater than 0 for all of the variables, I'd be at a max. What do you think?
I think life might be more complicated than that.
How can you say that to me, Rahana? You've just like...
Let's look at a function.
All right, what do you think we should look at as a function?
You want to try f of xy is x times y?
Okay, let's try f of xy equals x times y. Well, that's actually an interesting function, because where does that have a minimum or a maximum?
Does it have a minimum?
I don't think it has a minimum or a maximum, right? Because if I think about, so here's x, and here's y, and here's f of x comma y, right? If I sort of think about this as a surface, pretty clearly it's going to be positive whenever x and y are positive. It's going to be negative whenever x and y are negative, or it's going to be positive whenever x and y are also both negative. Why did I draw this way? This is a terrible way to draw this. Let's go to another sheet of paper. So if I think about a contour plot of this, let's think about a contour plot as this. So here's x and here's y. Pretty clearly, if I say f of x comma y is x times y, that's equal to 0 along this line, right? Because x is 0. It's equal to 0 along this line. It's positive when I'm up here, because both x and y are positive. It's positive when I'm down here. They're both negative. It's negative here. It's negative here. So this function actually goes down like this and comes back up. And while you can't see that on the webcam at all, so it's sort of goes down and then back up, but here it comes up and then comes back down, right? So at the origin, we actually have a saddle point here for this function. Okay. Well, that seems to me, I want to push on that function a little bit, because it seems to me that this function doesn't satisfy this condition, right? The partial with respect to x squared is 0 for this function, and the partial with respect to y squared is 0 for that function. So we have a saddle point, but it doesn't seem to violate the condition.
No.
Maybe we should think about another function.
All right.
So here I've got a function I'm going to pull out of my hat. Here's a beautiful MATLAB plot. Isn't that a beautiful plot? Look at that. That's like gorgeous. But let's look at this function for a second, and let's think about what are the partials of this function, right? So what if I'm at the origin? Here's the origin. What's the partial of this with respect to x squared? So let's say that's the x-axis, so x is increasing in that direction, y is increasing in that direction. So what's the sign of partial of f with respect to x squared?
Well, it looks like it's concave up, the slice
Yeah, it looks like it's going up, right? This is like a parabola going along x, so it's greater than 0, right? And I think that's also greater than 0, right? But if I look at this point sure doesn't appear to be a max or a min.
Nope.
Right? It's a saddle point. So we've got a bit of a problem, I think, right?
So life is more complicated.
Life is more complicated, as you suggested. I think you might have known where we were going with that. So this suggestion is what we call nonsense in the technical space. Let's just call it nonsense. And in the next video, we're going to show you a way of getting out of that hole.